Okay, finally, we are on the last topic for this unit. So, electron configuration. Now, I'm going to talk about a lot of things in this video, and not all of it that you necessarily need to know as far as for testing, but it's important to kind of conceptually understand it, so I'm going to go over it anyway. So, we'll start with the objectives, pause, and peruse if you wish. So what is electron configuration? Well, it's the arrangement of electrons in an atom. So what does that mean? Well, let's get to it. Okay, so we use the periodic table to find the electron configuration, and this really is the basis for the testing as far as this class goes. So you look at the electron configuration. Remember, the last number is the number of valence electrons. Okay, first big idea, electrons are in a specific energy level. Remember when we talked about emission spectrums, how we talked about when an electron moves from the excited state back down to the ground state, like going from the 5th energy level to the 2nd. Okay, electrons exist in a specific energy level, and the ground state configuration is what is shown on the periodic table. So the periodic table gives us information about the energy levels, but again, it's information about ground state. All right, so what does the periodic table tell us? Let's talk about the period number first. That's the rows. So look right here. So you see period, and then you see 1, 2, 3, okay, all the way down to 7. All right, so what does that tell us? It tells us the highest energy level that the electrons are in. So elements in period 1, so starting with hydrogen, only have electrons in energy level or shell, sometimes it's called that, 1. Elements in period 2 have electrons in energy level or shell 1 and energy shell or level 2. So when I get down to period 7, so francium, the first element here, it's in period 7, which means it has electrons in energy shell number 1 and energy shell number 2 and energy level number 3 and energy level number 4 and energy level number 5 and energy level number 6 and energy level number 7 because it is found in period 7. Let's look at a specific element and get some more details. Okay, so this is cesium, atomic number 55, which means it has 55 protons and 55 electrons. The 2, this first 2 right here, this 2, means there are 2 electrons in energy level number 1. This 8 means there are 8 electrons in energy level number 2. This 18 means there are 18 electrons in energy level 3. The next 18 means there are 18 electrons in energy level 4. This 8 means there are 8 electrons in energy level 5. And this 1, there's 1 electron in energy level 6. And since it's the last number, we already learned, that's the valence electron. What energy level are the valence electrons in? So look, valence electrons is the last number, right? Okay, so now this is energy level 1, energy level 2, energy level 3. Oh, the 4th energy level. What period is this element in? Well, first you could hunt it out on the periodic table and look across, but we can figure it out anyway. Remember, the period is the number of energy levels. So how many energy levels does this have? Well, it has 1 energy level, 2, 3, 4 energy levels, which means it has to be found in period 4. The electrons are in a specific orbital. Okay, now here's where all of these details you don't need to know, just conceptually you should understand it. Okay, there are sublevels with specific orbitals. So there's S sublevel, P, D, and F. Those are the sublevels. And they each have a certain number of orbitals. And you notice they're all odd numbers, and you just have to remember the order, S, P, D, F, and it's 1, 3, 5, 7 for the number of orbitals. Again, a lot of these details are not going to be tested, but just conceptually it's important to understand. And the electrons are arranged in these orbitals. So you see the S orbital, right? S sublevel has 1 orbital. The P sublevel has 3 orbitals, and you see they're kind of dumbbell shaped. And the S orbital is sphere shaped. Then you look at the D orbitals, right? The D sublevel has 5 orbitals, and you could see the shapes get weirder, right? More complicated. And then the F orbitals, the F sublevel, remember, has 7 orbitals. They look the most complicated. And remember, an orbital is where you are most likely to find an electron, the highest probability. And remember, they have fuzzy borders. So what happens is energy level number 1, we're going to have an S orbital real close to the nucleus. And energy level 2, we're going to start with S. It's going to be a little further away, but then we're going to add P, okay, and so on. The periodic table gives information about orbitals, surprisingly, but you have to remember it. So here, the way the periodic table is set up, the S block includes the groups 1 and 2. Now, helium is all the way over here in group 18, but really it's part of the S block because it should be right there next to hydrogen. The reason it's put all the way across is because its properties match with those elements in group 18. It's kind of a little bit of an oddball. And then the P block is groups 13 through 18. D block is in the middle, and then F block is at the bottom. Now, it doesn't say this anywhere in the periodic table. You got to know it. And those inner transition elements, if they're actually where they belong in the periodic table, it looks like this, okay? So S, P, D, and F, okay? So that was lanthanides and actinides, that F block. It doesn't really exist at the bottom. The reason it's put at the bottom is just to make the periodic table fit on a regular sheet of paper easier, the symbol's big enough. Each orbital can hold 2 electrons, and those electrons are spinning in opposite directions. So one electron spinning this way, the other one spinning this way, okay? So S sublevel has 1 orbital, so it can hold 2, okay? So the S sublevel has 1 orbital, it means it can hold 2 electrons. P, there's 3 orbitals, so that means 6 electrons. D, 5 orbitals, 10 electrons. F, 7 orbitals, 14 electrons. So conceptually, you should understand that each orbital can hold 2 electrons, and those electrons are spinning in opposite directions. This diagram, which we are not going to work on actually placing those electrons, but if we were, you see how there's one going up and then one going down? That's how you would represent electrons spinning in opposite directions. And remember how when we did Lewis dot structures, how we put 1 dot around each side before we doubled up? In those kind of electron configurations, you have to do it the same. So each box for 2p, for example, would get an arrow going up before any of them got an arrow going down. Okay, so same kind of concept. Electrons fill the lowest energy level first. I kind of like this picture as a way to represent the order that the orbitals are filled and which energy level. So do you see all the S's are written across, all the P's, all the 2's are in line vertically, all the 3's, all the 4's, and so on, okay? And then it just goes S, P, D, F like normal. Remember S1, energy level 1 only has S. Then we add P, then we add D, then we add F, and we don't go beyond that. Well, for now anyway, according to what we know. Now watch the arrow. So that means electrons fill 1s first, and then you draw these zigzags. So then 2s, then 2p, then 3s, then 3p. All seems normal, 4s, but then I'm going to circle back, and then I fill 3d before 4p. Okay, so I really like this visual right here, this one, to represent the order that orbitals are filled. Here it is represented another way, which involves a lot of memorization. This way, you don't really have to memorize. But also, the periodic table will help you. So if you remember the S, the P, the D, and the F blocks, as you go across, you say, oh, 1S, then I go to atomic number 3, 2S, 2P, 3S, 3P. Why is it 3? That's period number 3. Then 4S, but now I don't fill 4P yet. I go 3D, okay? So the periodic table can help you. Okay, let's try and put it all together. Okay, let's look at this. Energy level 1 has s orbital only, 2 electrons because there's 1 orbital. So energy level 1, 2 electrons. Energy level 2 has s, but adds p, and p holds 6 electrons. Remember, p was groups 13 through 18, 6 boxes, but altogether we still have 2s over there. So altogether, energy level 2 holds 8 electrons. Now energy level number 3 has s, has p, add d. Okay, but D has 5 orbitals, which holds 10 electrons. So add all those up, energy level 3 can hold 18 electrons. Now when we get to energy level 4, we have S, we have P, we have D, now F. Okay, and F has 7 orbitals, so that's 14 electrons. So add that up, and it can hold 32. Okay, now energy level 5 has S, P, D, F as well. Okay, and continue all of the energy levels that we know. We don't go beyond F. All right, so looking at the periodic table, you could see 3s1, 3s2, so 3s1 sodium atomic number 11, that's what's being filled, 3s1, then 3s2. Okay, so those numbers at the top represent the number of electrons in that sublevel in those orbitals. Okay, so why do electrons fill 1s before 2p? This should be a basic rule, and you absolutely should understand this. Because 1s has less energy. Electrons always fill the energy levels with less energy first. Electrons must fill orbitals, and in this case, energy levels, right? 1 goes before 2. But electrons have to fill the orbitals with less energy first. Remember that zigzaggy line diagram? What orbital is filled after 3s? So you could draw that zigzaggy, or you could look at the periodic table if you remember S, P, D, and F. But it would be 3p. After 3s goes 3p. What orbital is filled after 4s? It's 3d. If you remember from the periodic table, K, potassium, is atomic number 19, that's 4s, then calcium, and then we go across and we're in D block, and D block counts 1 behind, F block counts 2 behind. But again, you don't have to remember all these details because you aren't going to be tested on them in this class. I just like to conceptually throw it out there. And which of the following represents an electron configuration of a calcium atom whose atomic number is 20? So what you should do is add up these numbers. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6, 18, 19, 20. So that's 20 electrons. Let's check this one. 4, 10, 12, 18, 21. All right, I'm going to keep adding and check and see the representation. So look here, this is 4, 10, 11, 12, 13, 14. This is also 20, but why is this wrong? I'd have to look at the periodic table because it has to match the energy levels, okay? So where calcium is, I should have only electrons up to energy level 1, 2, 3, 4. And this has 1, 2, 3, 4. Okay, that's fine, but calcium does not go into 3D right here. This, also see right here, 3s should be filled with 2 before I put anything over here, okay? And this does not have 20. there you have it. That's probably the toughest question, and you probably won't even really see it on the periodic table except to be looking for total numbers of electrons. Okay, so I hope that you learned something new today.